Hey everyone, and welcome to the AI Research Roundup. I'm your host Alex, and as always, we're here to chat about the latest in AI research. Today we're looking at a paper titled LatentSync, Audio-Conditioned Latent Diffusion Models for Lip Sync. This one was published around December 12th, 2024. So, the core idea here is a new end-to-end framework for lip sync. It uses latent diffusion models conditioned on audio, which is a bit different from previous approaches that worked in pixel space or used two separate stages. They also introduce a technique called TREPA to improve how consistent the video looks over time. And speaking of the details, the researchers have actually made their work pretty accessible. What we're looking at here is their official GitHub repository for LatentSync. It seems like they've included, well, the inference code, the model checkpoints, and even scripts for the data processing and training pipelines. So if you wanted to dig in and reproduce it or build on it, it looks like the resources are there, which is always great to see. Okay, so this figure here, figure 1, it actually gives a nice visual comparison of the different approaches. You can see in panels and how previous diffusion methods worked. Panel is pixel space diffusion, taking the audio and reference frames straight into the diffusion model. Panel shows a two-stage method, predicting motion first, then rendering. But Panel shows LatentSync's approach. It uses a VAE encoder to go into the latent space first, applies the audio-conditioned diffusion there, and then decodes back. This is that end-to-end latent approach they mentioned, aiming to be more direct. Okay. So figure 2 here digs a bit deeper into the LatentSync architecture itself. We see the inputs more clearly now. The masked frames, reference frames, and the audio, which goes through a whisper encoder to get embeddings. What's interesting is how they combine things. The visual latents are concatenated channel-wise with noise, and then the audio embeddings are injected using cross-attention within the main UNet structure. This figure also explicitly shows the training process, where the output is decoded back to pixel space to calculate those SyncNet LPIPS and TREPA losses against the ground truth. Alright, so moving on. Figure 10 here gives us the visual results, the qualitative comparisons. We can see how LatentSync stacks up against other well-known methods, like Wave Tulip Video Retalking Dinette and MuseTalk. The top row shows the target video, the person we want to animate, and the second row shows the source video where the audio comes from. Then, the following rows show the output from each method. LatentSync is the last row. So this lets us visually compare the lip sync quality and how natural the expressions look across the board. And looking at those visual results, LatentSync really does seem to produce quite natural-looking lip movements, doesn't it? I think the key takeaway is how this end-to-end latent diffusion approach can generate high-quality synchronized video directly from audio. It's definitely pushing the boundaries for creating more realistic digital humans and has loads of potential applications. Well, that's our time for today. Thanks so much for joining me on the AI Research Roundup. I'm Alex.